Bond polarity relates to the even or uneven distribution of electrons in a molecular bond. Also, bond polarity will contribute to molecular polarity. So we're going to take a look at these two concepts, both the idea of bond polarity and then how bond polarity contributes to whether a molecule is polar or nonpolar. To take a look at bond and molecule polarity, we need to revisit the concept of electronegativity, also known as electron hoggishness, or how well atoms tend to share electrons when in a covalent bond. We recall electronegativity. It's the tendency for an atom to attract electrons to itself when that atom is chemically combined or bonded with another element. The pattern on the periodic table, as we go across the periodic table, the electroactivity of elements tends to increase. And as we go down the periodic table, the electroactivity of atoms tends to decrease. Up in the top right corner, our most electronegative element is fluorine. Recall, when we call something a covalent bond is the sharing of an electron pair between two atoms. Sharing of electrons can be equal. Think of it as if you and a friend are sharing a pizza. If you share the pizza completely equally, the pizza gets split 50-50. You each eat 4 pieces of pizza from the pizza that you have. When the sharing takes place as equal, the bond is identified as being something we say is perfectly covalent. Sometimes the sharing can be unequal. Similar again to possibly sharing a pizza. You split, but one person eats 6 pieces when the other only eats 2 pieces. This would be an unequal sharing. When the sharing of electrons between atoms in a bond is unequal, we'd say the bond is something identified as being a polar covalent bond. In a perfectly covalent bond, our bonding pair of electrons is evenly distributed between the two bonding atoms. The electron cloud ends up being symmetrical. The bonding atoms that we have the exact same electronegativities. Therefore, the electron pair, the bonding pair, is shared 100% equally. Because the electrons are being shared completely equally, the electron cloud of the bonding pair is symmetrical, and this creates what we would say is a nonpolar covalent bond with the electrons being evenly distributed between the two bonding atoms. On the other hand, if we take elements of dissimilar electronegativity such as carbon and oxygen, sharing of electrons becomes unequal. The more electronegative oxygen atom draws the electron cloud more towards its end. The electron cloud, because the electrons are no longer evenly distributed, becomes non-symmetrical, with more electron density towards the oxygen end of the atom and less electron density towards the carbon end of the bond. So what we have here is, with oxygen being a more electronegative element than carbon, the oxygen pulls the electrons more towards the oxygen end, and with the electron cloud density shifting towards the oxygen end and making a non-symmetrical electron cloud, produce what is known as a polar covalent bond, in which the oxygen end of the atom becomes partially negative due to increased electron density towards the oxygen end, and the carbon end of the bond becomes slightly positive. The little symbol, the squiggly d, which is a lowercase delta, that just represents the charge there as a partial charge rather than a full-flown charge. And when we say something is polar, polar means that something has a positive negative end to the item, which we see here in our bond with a slightly negative end towards the oxygen and a slightly positive end towards the carbon end of our chemical bond. Now within bonding there's an entire spectrum, where at one extreme we have the perfectly covalent bond with the electron cloud evenly distributed around the bonding atoms. This would be when we have no difference at all in electronegativity between the bonding atoms. Typically, something's considered nonpolar if the difference in electronegativity is 0.0 up to about 0.4. When we start getting from 0.4 moving up in difference between electronegativities, we hit our first where we have what we call a slightly polar covalent bond. In this case, the electron cloud is starting to become slightly non-symmetrical. As the difference in electronegativity between bonding atoms continues to increase, the distribution of electrons, the bonding pair of electrons in the electron cloud, becomes less even. As the distribution gets more and more skewed and the cloud less and less symmetrical, the bond becomes more and more polar covalent. As the sharing continues to become less and less equal, up to a difference of about 2.0 between electronegativities of bonding atoms, we get what we would say is a highly polar covalent bond, and we can see that the distribution of electrons is getting less even, and the electron cloud becomes more and more skewed. Eventually, when the difference in electronegativity becomes more than 2.0, we no longer have a bond considered covalent. The bonds are now considered ionic. In an ionic bond, the sharing of electrons is stopped. There's no more sharing. One atom is completely stripped an electron away from another, and we now have separate positively and negatively charged ions. And the bond is from an electrostatic attraction of the positive-negative ions sticking to one another. Key thing is there's no more sharing. So up to an electronegativity difference of about 2.0, there's still sharing going on, although unequal. At the opposite end, with the difference in electronegativity of 0.0, we have a perfectly covalent bond. So in bonding, there's a spectrum. At one extreme, the perfectly covalent bond, and as we continue to increase our difference in electronegativity, bonds become more and more polar covalent. They start leaning towards becoming more and more ionic character, till eventually we cross a point where no more sharing takes place and the bond is considered to be ionic. Next, we need to take a look at how overall molecules can become polar. It's almost as though we'll be looking at somewhat of a tug of war between all the bonding pairs of electrons within the geometry and structure of the molecule to determine if the molecule is polar or nonpolar. Take a look at the molecule of carbon dioxide as an example. Using the periodic table, we can see that oxygen has a higher electronegativity than carbon because oxygen is further to the right on the periodic table. Looking at a table, more specifically, we can see oxygen has a value of 3.5, carbon has a value of 2.5 for their respective electronegativities. We can now use a force arrow or a vector to indicate that the oxygen is pulling electrons from the carbon towards the oxygen on the right, and similarly, in the exact opposite direction, oxygen is pulling electrons to the left. The size of the pull in each direction is based on the difference in electronegativities between the bonding atoms. We can say oxygen is pulling to the left, 1.0, and pulling exactly to the right, 1.0. Since carbon dioxide has a molecular geometry that's linear, the pulls from the oxygens in each direction are completely equal and opposite to one another. If we look at our force diagram, we can see the force diagram, the forces are going to cancel, given that they're equal and in opposite directions. Gives us a net force tugging on the electrons of 0. In chemical terms, we would say this means the molecule has a dipole moment equal to 0. And we would say the molecule as a whole is a molecule that is nonpolar. Next, let's take a look at the molecule H2O. The water molecule has molecular geometry we would identify as being bent. From the periodic table, we can say that oxygen is more electronegative than hydrogen atoms. This means the oxygen atom will be pulling the electrons in the bonding pair towards the oxygen in both of the chemical hydrogen to oxygen bonds. The electronegativity table shows us oxygen has a value of 3.5, hydrogen a value of 2.2. The size of our force arrows or vectors being pulled towards the oxygen with 1.3 and 1.3. Overall, our force arrows are pulling towards the oxygen. There's nothing pulling back in the other direction to offset the pull of the oxygen atom on our two covalent bonds, polar covalent bonds in the water molecule. Consequently, what this does, it makes the water molecule have the half, if we could cut it in half, the half towards the oxygen end becomes partially negative, the half towards the hydrogen end becomes slightly positive. With a positive and negative end to our molecule, we would say that this is a polar molecule. It's as though if you could approach the water molecule and take a look at it, looking towards the oxygen side, from that side the molecule would appear to be slightly negative. Whereas if you were to approach the molecule from the opposite side and look at the end with the two hydrogen atoms, from that end the molecule would appear to be slightly positive. Because we have this positive and negative ends to our molecule, we say the molecule is a polar molecule. Let's look at another molecule, CF4. Fluorine is the most electronegative element on the periodic table. So in all of these bonds, the fluorine will be pulling the electron density out towards the fluorine atom. So individually, every carbon-fluorine bond is a polar bond. Fluorine has an electronegativity of 4, carbon 2.5. Our difference here is 1.5. However, the pull in every direction on the fluorines is exactly the same, a pull of 1.5. All the orbitals in a tetrahedral structure are evenly distributed, 109.5 degrees apart. Consequently, all of these pulls of the fluorine atoms will cancel out, and even though the individual carbon to fluorine bond is polar, the molecule itself ends up being an example of a molecule we'd identify as being nonpolar. Merely change our formula slightly to CH2F2, replacing two of our fluorines with hydrogen atoms, and we change the entire polarity of the molecule. The two fluorine atoms are pulling electrons towards this end of the molecule, and the carbon is slightly more electronegative than the hydrogen. So this is also being pulled in towards the center. Overall, the electron density of the molecule is being pulled more towards the fluorine side. If we could look at the tetrahedral structure from the side of the two fluorine atoms, we'd see something that would appear to be partially negative, because the electron density has been pulled towards the fluorine side. Whereas if we could look at the molecule towards the hydrogen backside of our tetrahedral structure, we'd see an end that appears to be slightly positive, as the electron density has been pulled over the fluorine side. Because we have a positive-negative ends to our molecule, this is a molecule we would identify as being a polar molecule.